Hello there, it's Dr. B again, and I'm going to be teaching you all about measures of central tendency. And central tendency is just a single score or set of scores which define the center of the distribution or the trends in the data. And this measure of central tendency is supposed to represent all of the numbers in the data set. And the three primary measures of central tendency that I will introduce to you in this lecture are the mean, the median, and the mode. So you'll see those listed right here under topics. I will also introduce you to the concept of the weighted mean, which is just a special version of the mean when you want to combine two means from two different sized samples together. And then I will end with how you figure out what is the most appropriate measure of central tendency to use based on the type of variable you're looking at and the shape of the distribution. So the mean is just a fancy statistical term for the average. So we've all heard about the average before. And the way that you find the average, or the mean as we're going to be calling it from here on out, is you take all of the scores that you're interested in, you add them together, and you divide by the total number of scores that you added together. Then there's two different notations for the mean. If you're working with a sample, then the statistical notation for the mean is just M. If you're working with a population, then the statistical notation for the mean would be that little mu. That's what this little funky U looks like down there. But in both cases, you can see that the numerator is the sum of x, or the sum of all the scores that you're working with, divided by n, the total number of scores, the population or the sample size. So here's an example using a frequency distribution table of calculating the mean. And we're going to go ahead and call this a population. And let's say that we were looking at all junior psychology students at Nevada State College, and we asked them how long they've been attending college at NSC. So just a quick review of frequency distribution tables. This first column, you see the full range of the variable that we're looking at from highest to lowest, top to bottom. So the maximum value, the maximum number of semesters in this population was 10, the minimum was 1. And then the next column displays the frequencies, or how many students said they were here for each number of semesters. So when you add up the frequencies, this gives you the total population size, because if you think about it, one student said they were here for 10 semesters, 3 students said they were here for 7 semesters, all the way down. You want to know how many students were in the population, add those together to get your N. Then when it comes to figuring out the sum of x, you need to be careful. Don't just add up these x values in that first column, because that does not take into account how many times or how many students said they were here that number of semesters. So you need to create this fx column, take each x value, number of semesters, multiply it by its respective frequency, how many students were here that many semesters. And then once you do that for each line in your frequency distribution table, you add those values together and you end up with this 126. And I showed my math up here just so that you would get a sense of where the numbers came from. And I recommend that you do this as well when you're doing your calculations, because it makes whoever's grading your assignment, makes their life easier to find where you got your values from and then maybe give you some partial credit if you made a silly math error but your process was correct. So you can see that I'm using the mu symbol to represent the mean because I'm working with the population. And then I'm also, in my formula, my sum of x divided by n, I'm using a capital N in my denominator to represent I am working with a population, so population size is the uppercase N. So the sum of x, the sum of all the scores added together, was 126. Divide that by how many scores there were, 51, and you get 2.471. So what we could say is that the mean number of semesters that all junior psychology students have been attending NSC is 2.471. Now here's an example where we are not using a frequency distribution table and where we aren't using a population, but we are using a sample. Now I just want to quickly point out that sometimes students get confused. They think that if they see a frequency distribution table, that automatically means that the data comes from a population, and if they see the data written out just in this raw form, then that automatically means the data is coming from a sample. That's not the case. It's just that most examples Using population data, we'll put it in a frequency distribution table because it's a nice way to simplify large amounts of data. Typically, if you're working with the population, you have large amounts of data. But don't just assume that if it's presented one way that it means it came from a population or a sample. Okay, so that being said, let's work through figuring out the mean for this sample of junior psychology students. And let's say this sample comes from my statistics class. So if you count the number of numbers there, so we've got, let's see, 1, 2, 3, 4, 5, 6, 7, 8 values in our sample. So lowercase n, sample size, is equal to 8. You add all those values together, so 3 plus 2 plus 2 plus 2 plus 2 plus 1, and you end up with a sum of x of 14. And then you just plug those values into your mean formula. Notice that m represents mean, just a plain old m, not the fancy mu, because we are working with a sample. You'll also see there's a lowercase n in the denominator here to represent sample size. So you just add all the scores together, divide it by how many scores you had, and you get 1.75. Now remember, the mean for the population was 2.471, and there's a difference between the sample mean and the population mean, and that's an example of sampling error. So there's just a difference between the two. In most cases, even if we had a truly random sample, this is more of a convenient sample. Maybe I just sampled my particular students. But even if you had a random sample of all junior psychology students at NSC, you would still see a discrepancy between the sample and the population mean. And again, that is sampling error. Okay. So now I want to show you how to make the mean formula kind of backwards compatible to work for you to find other values that are related to the mean, that are in the mean formula. So remember, the mean is equal to the sum of x divided by n. Well, if you already know what the mean is and you know what n is, you can use the mean formula to find the sum of x. And this is going to be really useful for you when you use the weighted mean formula. So it's important that you understand this concept. So one way that you can think about it is, algebraically manipulating the mean formula to work for you. I usually start off by just plugging in the values that I have based on the original mean formula. So m equals sum of x divided by n. So I know what m is, it's given to me, so I replace m with 1.75. I know what n is, that's given to me, it's 8, so I just replace n with 8. And then I leave sum of x as sum of x. Because I don't know what that is yet, I need to figure it out. So in algebra, we typically try to isolate the value of interest on one side of the equal sign, and then we have, whatever we're interested in equals all the other values. So that's what I did here. So the first step that we want to do is we want to eliminate this fraction, this divided by 8. And the way that you eliminate division, so if we're dividing by 8, we want to get rid of it, we multiply both sides by 8. So that's an algebraic concept that you may or may not remember from the last time you took an algebra class. You basically just do the inverse operation to both sides of the equation. And it doesn't change the overall value of the equation, but it gives you the desired effect of getting rid of whatever you're trying to get rid of. So if we multiply both sides by 8, then this becomes, so we multiply the right side of the equal sign by 8, so the divided by 8 disappears. And then if we multiply the other side of the equal sign by 8, we're left with 1.75 times 8. So you can see that there. And I just kind of flipped the order because I like having something equals, the thing I'm interested in equals whatever values I'm going to be manipulating. So we're left with sum of x equals 1.75 times 8. Take 8, multiply by 1.75. And you end up with 14, and that is our sum of x. Luckily, you don't have to go through this thought process to find the sum of x based on the mean and the sample size or the population size. You can just play with the formula the same way that I did above, and just remember what the formula becomes, and just use that. So instead of plugging in my numeric values into the original mean formula, I'm going to keep it in variable form with these letters here, and just play with it until it ends up being something equals sum of x. So multiply both sides by n, right? We're trying to get rid of the n on this side of the equal sign because we want to isolate the sum of x. And you end up with sum of x equals m times n, and you plug in your values, you get the same answer. So On your formula sheet, you will see sum of x equals m times n, and that's just a simple go-to formula for figuring out the sum of x based on the mean and the sample or the population size. Well, just like we were able to use the mean formula to find the sum of x when we have the mean and the sample or the population size, we can find the sample or the population size when we know the mean and the sum of x. So this is kind of the same process that I showed you before. You can plug in your values and then manipulate it algebraically to end up with a final number. So you start off with the mean formula, you replace the mean with what the mean is, 1.75. Replace sum of x with what the sum of x is, because we know it already, 14, and then divided by that variable n that we don't know yet. So then the first thing I want to do is get rid of the fraction. So I'm going to multiply both sides by n. You end up with 1.75n equals 14. And the next step is I want to go ahead and get rid of this 1.75 because I want to isolate n equals something. So whenever you're trying to get rid of something that's multiplied by something else, you divide by it. Remember the inverse operation. So now if I take 14, divide by 1.75, I end up with 8 as my sample size. Or you can just make the formula work for you without inserting any values and just use the simple formula of n equals the sum of x divided by m. So before I move on to the weighted mean, I just wanted to go over some interesting properties of the mean and basically what happens to the mean when you start toying around with the scores in the data set. So if you add a score to the data set, and I put the little x there to remind you that x is just a placeholder for a score, then that's going to change the mean. The only time that adding a score to the data set will not change the mean is when the score equals the mean. So whenever you're adding a score to the data set, the formula that you can use to calculate what the new mean would be to take the sum of x, the original sum of x, and add the new score, and then divide that by your sample or population size plus 1. So you're basically adding the score to the sum of scores in the numerator and adding the fact that you have a new score to the sample or population size in the numerator. Now remember that formula that we just found to find the sum of x when you have the mean and the sample size, you take the mean times the sample size, or the mean times the population size if you're working with a population, and then you can use that as a replacement for sum of x. Because you may not know what the sum of x is, you may know what the original mean and sample size was, and then you can find the sum of x using that information. So same formula, it's just you're replacing sum of x with the formula for sum of x when you know the mean and the sample or population size. So for example, remember I said that if you add a score that equals the mean, it does nothing. So if you have 10 scores in your sample and it has a mean of 5, then you add one score of 5 and your mean is still 5. But let's say that you have that same sample and you want to add one score that equals x equals 16. Well, then you need to use that formula that I gave you before. And I use the second version of that formula because, in fact, I know what n is, I know what m is, I don't know what sum of x is. But by plugging in my sample size of 10 multiplied by my mean of 5, if you look in the next step, you'll see that I know my sum of x is 50. So I take that 50, my sum of x, I add my value of my new score, which is 16, and then in the denominator, I know my sample size was 10, plus that new score, plus that one new score gives me 11. And I end up with 66 divided by 11. My new mean is 6. So the mean jumped up by one whole point just by adding a new score, and that's because the new score that I added was rather large. Now what if I want to subtract a score from my data set? Well, that will also change the mean, unless the score that you're subtracting is equal to the mean. So if you want to subtract a score, the formula looks quite the same, except all of the plus signs are replaced by minus signs. So you'll see the sum of x, the original sum of x, minus the new score, divided by the sample or population size, minus 1. Same process for finding the sum of x based on the mean and the sample or the population size. So the same thing holds true. If you're subtracting a score that's equal to the mean, nothing changes. But as you can see in that second example, let's say we have that same sample of 10 scores, they have a mean of 5, and now this time we're subtracting a score of 16 instead of adding it. So in the numerator, we find the sum of x, 10 times 5 is 50. We're getting rid of that score of 16, so we subtract 16. Then in the denominator, we had 10 scores, we took one out, we're left with 9 scores. And so we end up with 50 minus 16 is 34, divided by those 9 scores. 3.778 is our new mean. And it dropped quite a bit because we took a very large score out of the data set. So it went from 5 to 3.778. Now I want to discuss the other property of the mean, which is if you do something constant to all of the scores in your data set. So if you change the value of each score in your data set in the same way, that will also change the mean. Now this is quite easy to calculate because if you do something consistent to all of the scores in your data set, the mean will just change in that same way. So you can see, if you add, subtract, multiply, or divide each score by the same value, then you just do the same to the mean. So if you had a mean of 5 and you subtract 3 from each score, you just subtract 3 from the mean and that's your new mean. So 5 minus 3 is 2. Or if your mean was 5 and you multiplied each score in your data set by 2, you just multiply your mean by 2. So 5 times 2, and you know that your new mean, if you calculated it with all those scores that were each multiplied by 2, your new mean would be 10. Okay, so moving on to the weighted mean. So the weighted mean is really useful when you want to combine two or more sets of scores. So you can see that this formula here really just represents a situation when you have two scores. So if you look at the formula, you'll see the little subscripts, the 1 and the 2. That represents the sum of all scores for sample or population 1, the sum of all scores for sample 2. But if you had 3 scores, then your formula would look a little bit different. You would have sum of x1 plus sum of x2 plus sum of x3 divided by n1 plus n2 plus n3. So you can make this formula work for you based on how many sets of scores you are working with. For my purposes in this lecture, we'll assume we only have 2 sets of scores. And we're also assuming that we don't have access to the raw data. Because if we had access to the raw data, we could just combine the data, find the sum of x, divide by how many scores we have. Now I also put in here how you can find the sum of x if you're only given the mean and the sample size. So you could convert this formula to look like this, mean multiplied by the sample size instead of sum of x. And then you still have your n1 and your n2 in the denominator. So the weighted mean is important because sometimes it is necessary to combine 2 sets of scores with different sample sizes, and you only have access to the statistics for each sample, so you don't have those raw scores. You cannot simply add the means together, and you cannot even add the 2 means together and divide by the 2 to find the mean of the means, you could say. To find the correct mean when combining samples with unequal sample sizes, or in other words, the weighted mean, you must account for the difference in sample sizes. So one mean carries more weight than the other because it comes from more scores. So you can see that in the second version of the formula. Let's say that the sample size for sample 1 is smaller than the sample size for sample 2. Well, in the numerator, we're going to be multiplying the mean for sample 1 times a smaller number than the mean for sample 2. So the mean for sample 2 will have more influence on the final value of the weighted mean. And you'll see that pan out whenever you do problems like this. Let me show you an example. I'm going to X those out at the bottom because I said you don't add the means and you don't find the mean of the means. One thing I do want to point out before I show you this example, you could technically take the mean of the means if you had equal sample sizes, but if you're asked to find the weighted mean, chances are you do not have equal sample sizes, so be really careful with that. Okay, so here's an example. Let's say that we looked again at the number of semesters junior psychology students at Nevada State College were attending. And we look at my class and we look at Dr. Marshall's class. So 2 samples. And let's say I have 8 junior psychology students in my class, and again their mean was 1.75. And then Dr. Marshall has 10 junior psychology students in her Psych 210 class, but their mean is a 4. Well, if you look at the formula, it starts off with, the sum of x divided by n, but I don't have my sums of x, so I can use that second version of the formula that uses what I do have, the mean and the sample size. So M1, let's go ahead and treat my class, Dr. B, as group 1, and Dr. Marshall's class as group 2. So you just replace these variables with the values. So the mean for my class was a 1.75, so M1 becomes 1.75. The sample size for my class is 8, so N1 becomes 8. The mean for Dr. Marshall's class was 4, so M2 becomes 4. And the sample size for Dr. Marshall's class was 10, so N2 becomes 10. And then in the denominator, N1, my class, there's 8 students. N2, Dr. Marshall's class, there was 10 students. So then you just do your math. So order of operations, you need to multiply first. So take your 1.75, multiply it by 8, you get 14. Plus 4 times 10, 40. Now we've got our values for our numerator. And then 8 plus 10 in the denominator becomes 18. Then 14 plus 40 is 54. Divide that by 18, you have a weighted mean of 3. Now remember, I said that the whole point of the weighted mean is that you want the mean that comes from the larger sample to carry more weight or to be more influential in the final value. And guess what? Our final weighted mean of 3 is in fact closer to 4, the mean from the larger sample of 10 students, than it is to the mean of 1.75 that came from the smaller sample of 8 students. So that's a really great way to check your work. If you calculate a weighted mean and it's not closer to the mean from the larger sample, you know something has gone awry. So now let's shift focus from the mean to the median. And the median is simply the midpoint of scores. But be careful, before you find the median, you need to place your scores in numeric order. You can't just look at your data and go, oh, there's the middle. Again, it has to be in numeric order. Now the median also splits the scores in half. Once you find the median, you'll always know that 50% of the scores are below the median and 50% of the scores are above the median. Again, it's the midpoint. Now there's a nifty way to find the location of the median using something called the median index. I believe this is not in your textbook. So to find the median index, which is symbolized as I, you just take your sample or population size, I'm just going to stick with sample size notation here, and you split it in half, divide it by 2. If you end up with a value for I that's not an integer or is not a whole number, this happens when you have an odd number of scores, then you only have one midpoint, and you take I and you round it up, and that tells you the location of the median. And I'll show you examples for this. Now, if you have a situation where you have an even number of scores, when you find I, n divided by 2, you will end up with a whole number. However, that's not going to mean that you just have that one location. You have to take 2 midpoints. So you take the location at I plus the location at I plus 1, and you divide it by 2. You essentially find the average of the 2 midpoints, and that gives you the median. So this may seem complex at first, but once I go through a few examples, it should make a lot more sense, and this will help prevent you from making mistakes, especially when you're using a frequency distribution table to locate your medians. So here's an example where we have an odd sample size. And remember before, if you have an odd sample size, you're going to have one midpoint. Again, if you have an even number of scores, an even sample size, then you'll have 2 midpoints and you have to find the average of them. So we have 9 scores in this sample. If you look up at the first presentation of the data, it's not in numeric order, so a good first step is to always place your scores in numeric order if they aren't already. And then you figure out what I is. So I, n divided by 2, n is 9, 9 divided by 2, 4.5, round up to 5, see here, ith score, round up, and 4.5 rounds up to the 5th score. Now be careful, that does not mean that your median is 5. That means that the location of your median is the 5th score from either the bottom or the top in numeric order. You can count however which way you want. So this also tells me that I know there's going to be 4 above and 4 below my median. So You place your data in numeric order, so you can see that top row there. My data is in numeric order. And then you can count 1, 2, 3, 4. Oh, there's my fifth score, number 3. You could also go from the low end over, so starting from the right, the right to the left, and you could say, okay, 1, 2, 3, 4, fifth score. It does not matter which side you start counting from to find the position of the median, because it is the midpoint. So if you start at the low end, it doesn't matter. If you start at the high end, it doesn't matter. You'll get to the same midpoint. So here's an example where we have an even sample size. So we're going to have technically 2 midpoints, and then we need to find the average of those 2 midpoints to get the median. So now we have 10 scores. You still want to place your data in numeric order, which you can see in that top column there. You still use I equals n divided by 2, but remember, you're going to have to find the average of the 2 scores at the 2 midpoints. So 10 divided by 2, sample size is 10, divided by 2. So we know that the first midpoint is the 5th score in numeric order. And then the next midpoint will be the next score. So 5th plus 1 would be the 6th score. And so we find the score that's the 5th score in our data set and the score that's the 6th score in our data set. So if I'm starting at the high end and counting in, so the 6 is the first, then 5 second, 5 third, 4 fourth. Oh, 5th score is a 4, 6th score is a 3, so I replace 5th and 6th score in that formula with 4 plus 3. Now again, if you counted from the low end, that's fine. You would go, okay, 1 is the first, 1 is the second, 3 is the third, 3 is the fourth, 3 is the fifth, and 4 is the sixth. You'd still end up with 4 and 3 as your 2 median, your 2 midpoints. So then you find the average of those 2 midpoints added together. So 4 plus 3 divided by 2 becomes 7 divided by 2, and the median is 3.5. Okay, now let's do an example using a frequency distribution table to find the median. So in this case, we have an odd number of scores, so that means that we are going to have a single midpoint. We don't have to find the mean of the 2 midpoints to figure out what the median is. And we're still going to use that I, that median index, of n divided by 2. Well, in this case, our population size is 51. 51 divided by 2 is 25.5. We round that up to 26. So our single midpoint is going to be the 26th score, either from the low end or the high end. Remember, you'll end up with the same score, no matter what. So the 26th score is 1, and that's our median. And we have 25 above and 25 below. Now, the way that I found 1 to be the 26th score, well, it's easier if you start at the end that has the highest frequencies in it. So if you look at the frequency distribution table, the vast majority of students had only been here for 1 semester. So in looking at that, 27 students at 1 semester, well, the first 27 scores are 1. That includes the 26th score. So that's our median. Now, if we wanted to go from the other end, remember you could go from the low end or the high end to find the location of the score. So if I start at the top, so the first score is a 10. The second, third, and fourth score are 7s. The 5th score is a 6th. The 6th, 7th, 8th, and 9th score are 5s. The 10th score is a 4. Then all the way up to the 20th score is a 3. To the 24th score, that's a 2. And then all the way to the 51st. So the 24th through the 51st score are 1s, and that includes the 26th score. Here's an example when we have a situation where we have an even population size. So we're going to have those 2 midpoints that we need to find the mean of to locate what the median is. So using our median index of n divided by 2, 52 divided by 2 is 26. So we need to find the mean of the 26th, and then remember, ith score plus the ith plus 1 score divided by 2. So the 26th score plus the 26 plus 1, 27th score, finding the mean of those. So dividing that by 2. And in this case, both the 26th and 27th score are 1. So 1 plus 1 is 2, divided by 2 is 1. Again, you could count from the high end of the distribution if you wanted to, but if you start with the end of the distribution that has the highest frequency, it saves you some time. Okay, so now let's move on to the mode. Now the mode is probably the least complicated measure of central tendency because you simply look for the score or scores that occur the most often or that have the greatest frequency. So there's a couple of ways that you can look for this. You can look for the x value with the highest value for f, so the highest frequency in the frequency distribution. You could also look for the tallest bar in a frequency distribution graph. And the tallest bar corresponds to the value with the highest frequency. Keeping in mind that you can have more than one mode or more than one value that occurs more frequently than all the others. Or most of the others, I guess, if there's multiples. Okay, so here's an example of what I just told you, how to locate the mode. So if you're looking at the frequency distribution table, simply look in the F column, find the highest number or numbers, and then look for what value, what score those frequencies correspond to. Well, in this case, we have a pretty clear winner for what is the mode. 27 is the highest frequency above all other frequencies, and that corresponds to a number of semesters or a score of 1, so the mode is 1. If you plot this out in a frequency distribution graph, you can see that the bar corresponding to one semester is far taller than all the rest. We know that is our mode. Remember, you can have multiple modes, so maybe we had another number of semesters with exactly 27 as our frequency. But you can also say that you have multiple modes if maybe you had another value in this data set. Maybe we had 24 students who had been attending NSC for 5 semesters. Well, you could make the case that you have 5 and 1 as your modes. It depends on who you're asking. Some people say you have to go with the absolute highest frequency and all matching frequencies that are that high. And some say if there's a couple that are way higher than all the rest, you can say that you have multiple modes. And the case for that is that if you have multiple peaks in your distribution, even if the peaks aren't the same exact height, we call it a bimodal or a multimodal distribution. So I showed you all 3 measures of central tendency, and I showed you all 3 for a reason, because there's different situations where a particular measure of central tendency is most appropriate. And that all depends on the scale of measurement and the shape of the distribution. So here in a little bit, you'll understand why this cartoon is funny. It's because the mean can be biased by really high scores. So the mean uses every single score in the distribution and is very closely related to measures of variability, so the next chapter that you'll be seeing. So the mean is always preferred and always used in inferential statistics, even if we have a situation where the mean isn't the most appropriate measure of central tendency. However, the mean cannot be calculated when you have open distributions. So if you have an open-ended distribution, so for example, if I said, how many semesters have you been at NSC? But I restricted it to you've either been here for 1, 2, 3, 4, or 5 plus. Well, 5 plus could be anything greater than or equal to 5. So if we had that in a frequency distribution table, so if, for instance, we had 1, 2, 3, 4, 5 plus, and in 5 plus we would have, let's see, 4, 5, 6, 7, 8, 9. We wouldn't have access to all the values in the data set, so we could not find the sum of x. And the sum of x is pretty important when it comes to finding the mean. So you would not be able to calculate a mean if our data was presented and there was an open-ended distribution. The mean also cannot be calculated when we have grouped frequency distributions. So remember when I talked about grouped frequency distributions in the last video, I discussed how sometimes they aren't really ideal even if you have a large range of values in your data set because you do lose richness of information. So with the grouped frequency distribution, the sum of x is incalculable because let's say you have, I'm looking at from 10 to 19, I have 4 scores. Well, you don't know the exact value of those scores, so you can't figure out the sum of x. Also, the mean can make no sense if we have nominal or ordinal data or discrete variables. So an ordinal scale, remember, just tells you the direction, not the distance of the differences between scores. And a nominal scale has no measure of quantity whatsoever, so neither the distance nor the direction are present within that type of variable. And then discrete variables, remember there's no interval between whole number responses. So just want to give you a quick review of ordinal, nominal, and discrete. And those are not appropriate types of variables for the mean to describe. Think about discrete variables. The mean can equal a decimal, and decimals don't really make sense when it comes to discrete variables. So if you see the census data and it says the mean children per family is 1.83, well, not really. I mean, you can't have a fraction of a child, so maybe the mean isn't the best measure to use. And here in a minute, I will talk about when it's appropriate to use the median and when it's appropriate to use the mode. Now, it is important again to mention that sometimes the mean is used with discrete variables on an interval or ratio scale, especially when variability is involved, because again, the mean is used for variability. So when we talk about variability, the mean is the reference point. So variability is just a fancy word for spread, and whenever we talk about this for the spread of scores, we talk about the spread relative to the mean of all the scores. So as this semester progresses, you'll see that we are calculating the mean when if we were purely looking at descriptive statistics, the mean wouldn't be the most appropriate, but for inferential statistics and for measures of variability, the mean is what we use. So I just wanted to point that out to you guys. So another consideration when it comes to, it's not just the scale of measurement, but it's also the shape of the distribution. So whenever you have a situation where you have outliers in your data set or you have a skewed distribution, you do not want to use the mean. And that's because those high scores are going to have a severe impact on the value of the mean, and then the mean is pulled towards those outliers and is no longer an accurate representation of the data. So if you have a normal or rectangular distribution and you have scale that's interval or ratio, you can go ahead and use the mean. So when to use the median for descriptive purposes. So when you have data that's on an ordinal scale, go ahead and use the median. And when you have a grouped frequency distribution, the median is appropriate. And then remember, I said that in order to use the mean, you have to have data that's on an interval or ratio scale and that has a normal or rectangular distribution. Well, if you have data that's on an interval or ratio scale that has a skewed distribution, go ahead and use the median. And I'll show you pictures of this, the shapes of distributions and the measures of central tendency here in a minute. So when to use the mode. So the mode is really the least descriptive type of measure of central tendency because it's really just focused on a couple of scores or a single score that have a high frequency without taking any of the other scores into account. So it's kind of our last ditch option when we have a situation where we have discrete data or we have data that's nominal. So if you think about nominal data, like for instance, if we were looking at class major, well, you can't put major into a meaningful order, so the midpoint, the median, would make no sense. The values aren't numeric in nature, so you can't calculate a sum of x to figure out the mean, so we would use the mode. So you could say the most frequent major among all students in Psych 210 is psychology, for instance. So with open-ended distributions, you can also use the mode because it's not that important that you don't know the exact values in your data set, but you could have a situation where the mode is 5+, right? And then you are losing some richness of information. Also, if you have a bimodal distribution, the mode is a more accurate representation of the data, and I'll show you why here in a little bit when I look at shapes of distributions. So let's go ahead and shift our focus to shapes and measures of central tendency. So remember from this data set that we looked at before, looking at the number of students in the population and how many semesters they've been at NSC, remember the junior psychology students, the mean was 2.471 and then the median and the mode were 1. So in looking at this distribution, you can see that the mean isn't very reflective, right? It doesn't really reflect the true tendency of our data. And that's because we have like a couple students with 10 semesters, a couple with 7, and those outliers are making the mean increase, go up. The mean is being pulled towards those outliers. So the mean overestimates the true nature of our data in that most students attended NSC for 1 semester. So this is a situation where we have a skewed distribution, positive skew to be exact, but our data is a ratio scale. So we would want to use the median. We have data that is on a ratio scale and it's skewed. Now, here's a situation where we have a normal distribution. So if we were looking at weight among a population, well, most people fall, in the middle, and then some are really heavy and some are really light. So this is a situation where we have a normal distribution and we have an interval scale of measurement. You could maybe make the case that this is ratio, although I don't know if the 0 point is true. I don't know. If you're 0, you're probably not being weighed in the first place because you don't exist. So in this case, regardless, we would want to use the mean because we have a normal distribution and either interval or a ratio variable. And you can also predict the location of your measures of central tendency based on the shape of your data set. So in this case, you can see that the mean, median, and mode are all approximately in the same place. So in addition to plotting out your data to figure out what the shape is, if you calculate your mean, your median, and your mode, and they're relatively close to one another, you know that you have a shape that's roughly a normal distribution. So here's a rectangular shape distribution. So maybe I have 4 children and their IQ scores are, one is 100, one's 101, another child is 102, and another child is 103. That would give me a rectangular distribution where we have a situation where there is no mode because there's the same frequency for all values in the data set. Well, in one of those cases, your mean and your median would be the same. And you could go ahead and use the mean in that case, assuming that your variable was interval or ratio scale. So you can see I've underlined the appropriate measure of central tendency in this graph. Here's a negatively skewed distribution. Now it's important to point out that we don't consider the shape of the distribution unless we have interval or ratio data. Because if we have nominal data, the shape is meaningless and we know we use the mode. If we have ordinal data, we know that we use the median regardless of the shape of the distribution. So again, you only consider the shape of the distribution when you have an interval or ratio scale. So something that would be a ratio scale would be the final grade in Psych 210. And believe it or not, my distribution typically looks close to this in my classes. So that's kind of nice, right? Lots of people do pretty well. So in this case, we have a negatively skewed distribution and we have a ratio variable. So the preferred measure of central tendency would be the median. So much like with the normal distribution, you can predict what the shape would look like without actually drawing it out based on the values for your measures of central tendency. If you have a situation where your mean is lower than your mode, then you know that you have a negatively skewed distribution. And that's because those outliers on the low end are biasing the mean towards it. It's dragging the mean down. It's making the mean smaller. So your mean is going to be smaller than your mode, which represents the higher frequency part of your distribution. And your median is always between the two. And again, median would be the preferred measure of central tendency, skewed data on a ratio scale. Now let's look at a positively skewed distribution. So here's an example where we're looking at the relationship between the age of a driver and how many crashes they had this year. And based on this particular graph, it looks like the younger drivers make up the vast majority of the number of accidents. So we have a positively skewed distribution. As you can see in this case, the mean is actually higher than the mode because those older outliers in this data set are dragging the mean towards it, making the mean a higher value. And this case, again, we have ratio, well, you could say interval or ratio. I don't know if we have a true 0 point here. And so we've got, let's say, interval data that is skewed. We are going to want to use the median. Now think about how you can measure values when I show this next example. So here it appears that younger drivers have more crashes. Well, if you control for the fact that older drivers typically aren't driving as much, so they're probably underrepresented in terms of number of crashes. If you control for that fact by looking at crashes per 100 million miles driven, you see a quite different distribution. So this would be a bimodal distribution. And in this case, we have two modes. The mean and the median are roughly the same. And we would want to use the mode to describe this. And that's because, check it out, what if I said, okay, well, you know, the typical age of drivers who have accidents is 48. Does that really represent this data? Not so much, right? It's really just falling in between the two true values that are representing the majority of crashes when we control for how many miles are driven. So the way that you could interpret this based on the mode would be that younger people and older people, so really young and really older people, have more accidents than everybody else. So I hope that this lecture made you feel comfortable with the various measures of central tendency. And I hope that now you're able to identify when it's appropriate to use a specific measure of central tendency.